Assalamu alaikum. In this video, we will see the project of PID controller design and tuning for DC motors in MATLAB. The objective of this project will be a classical control strategy PID controller for the control of DC motor. We will determine the system transfer function and then we will design an PID controller to meet or exceed response requirements from first principles. Then we will apply PID tuning rules in Semling to meet response requirements. There are many tasks which I have done for this project. First task of this project will be system modeling. A common actuator in control system is the DC motor. It directly provides rotary motion and coupled with mechanical loads such as wheels or drums and cables. It can provide translational motion. The electric circuit of the armature and the free body diagram of the rotor are shown in the following figure. You can see this is load and this is translation motion, and this is the motor, and here resistance, and here inductor, here is a voltage. This is the design of DC motor with mechanical load. In the above figure, V is the armature voltage, I is the armature current, E is the back electromotive force EMF, R is the armature resistance, L is the armature inductance, and omega is the shaft speed of the motor. J is the equivalent inertia on the motor shaft. T is the driving torque generated by the motor, and TL is the resistive torque from the load. It is known that E is equal to KE multiply omega and T is equal to KT multiply by I, and TL is equal to KT multiply IN, where KE and KT are respectively the back EMF and torque constants of the motor, and IL is the equivalent load current reflected by the load torque TL to the motor armature. The physical parameter are, in general, the torque generated by a DC motor is proportional to the armature current I and the strength of the magnetic field B. Here we assume that magnetic field is constant and therefore the motor torque is proportional to only the armature current I by a constant factor KT. This is referred to as an armature control motor for a small motor. The armature inductance is small, just like is equal to approximately is equal to 0, and hence can be neglected. Also, at the start of the motor, E current is equal to approximately 0, ignoring the resistance torque. Your task Our task will be to develop the controller algorithm to control the rotation of the load, that is, to control the angular position of the DC motor with certain performance parameters. First, for the system modeling, drive the transfer function. We will drive the transfer function that will represent the relationship between the angular velocity and input voltage. Then find the transfer function that represents the relationship between angular position and input voltage, just like to open loop control system. After that, we will design the controller design with the help of PID controllers that can be incorporated in the closed model, which is shown in this figure, in order to meet a set of the time response related to requirement, just as example as overshoot. And in the system design, controller design, we will determine the simplified closed loop equivalent form of the overall system block diagram, which are presented in this figure. Our controller requirement will be like this. Maximum rise time should be 0.12 second. Overshoot MP less than 4.5%. Settling time just like error equal or less than 1%. TS less than 0.2 second. Steady state error of 0 per step. Then we will determine the gains, use standard transfer function or pole position method to calculate the proportional Kp, integral Ki, derivative Kd, PID controller gains for overall system. Then we will verify the gains calculated by the implementing the system assembly. Then we will discuss any trade-off for exceeding the response requirement presented in section. For example, what's happened to rise time if overshot MP goes up? We'll discuss the results when each of the above controller requirements goes up or goes down. Then we will see the trial error rules for PID tuning by using Ziegler-Nicholas approaches. The aim of this section will be demonstrate your ability to use the knowledge to learn new techniques. We will assume just like the if you will got a job in control engineering company, your manager will be will give you a task just like research the literature, find out about manual tuning rules such as Ziegler-Nicholas technique. Tuning rules such as Ziegler-Nicholas are difficult to implement on PID controller configuration. You will convert your system to a PID control configuration and apply a suitable tuning process for regular Nicholas tuning rules in order to meet the response characteristics outlined in section which we already discussed previous. We should give a concise overview of PID tuning method in this section and demonstrate the design control system by assembly. This is our project. I already done the project. I show you the complete details and answer of this project in the report which I already made. First of all, I introduced the project, the majority of uh, PMDC motor control algorithm are applied in the industry. The property of PMDC motors are linear and steady. There are numerous methods for controlling or altering it. The speed of a DC motor to get the desired results. Various control algorithms are used to control speed. Mathematical modeling of DC motor and PMD is necessary. Every control algorithm is suitable. DC motor are mathematically modeled. The engine, the fundamental equation of induced voltage source is used to model it. the EMF of the armature, the load torque, the total torque generated with the motor. We get the following results using the input and output functions. A DC motor's transfer function. DC motor utilize the following application just like industrial control system. PID and LQR are including in this vehicle. A tactic for control. These controls are used to alert the performance of DC motor speed control. PID is most widely used controller to this day due to its low cost and ease of use. Accurate parameters are essential for precise tuning. So, our first task is system modeling. We are applying KVL in armature circuit to design the system. Just like apply KVL in armature circuit. For this, V is equal to Ri plus L derivative of I over T plus C, which is even plus E. Then we will apply the Laplace transform. You know the Laplace transform V is equal to I into R plus L plus E. It's known that E is equal to KE multiply omega. Inserting above values in equation, V is equal to I into R plus L plus KE multiply omega. Then simplify this equation into this. We know that I is equal to I over R plus L into V minus KE omega. The torque developed in armature is given as T is equal to KTI. T is equal to KTI according to the torque balance equation. T is equal to TC plus J dot T omega dt plus B omega. The torque developed in armature is given as I is equal to torque by applying Laplace transform. T is equal to Tc plus omega into J plus B, and simplify this equation. It's known that omega is equal to d theta over d delta t, where theta is angular displacement. We know that it is also asked to find transfer function where angular displacement, where theta is angular displacement, theta. It's asked to find the torque function with omega and input torque C from equation 3. If load torque is 0, then omega is equal to 100 over 10 plus. It is the corresponding. If load is 0, 0 load. Open loop control system is T1 over can be modeled as under load condition using equation 1 the system can be modeled as. Now we do a system modeling in MATLAB. The system will model by as summing the torques according to the inertia and integrating the acceleration to given velocity. Also, Kirchhoff's law will be applied to the armature circuit. First, we will model the integrals of the rotational acceleration of the rate of change. Next, we will apply the Newton's law and Kirchhoff's laws to motor system to generate the following equation. We applied the Kirchhoff and Newton law to generate the following equation. So I designed this system in MATLAB. This is the input. You can see input. So the add function will add then inductance and integrator and resistance, just like this. Speed is equal to J. Speed is equal to so the voltage we designed system modeling in MATLAB by using these equations 3, 4, and then we will apply Newton law and Kirchhoff law to motor system to generate the more simplified equation, just like d square theta over dt square is equal to 1 over j kti minus b d theta over dt, just like here. This equation is shown here. Minus resistance plus voltage and minus ke d theta over dt. Ke d theta over dt is obtained by kt adding damping and then inertia and then integration, then we will got d ke over dt theta. Then we will add this, and this is a constant input and this is the add block and this is gain block. We add just like input, you will get input block here, and then you can search add block, you will get add block here, and then you will get gain and you will get gain block here. This is also gain block, and then we will modify according to our resistance. This is inductance. This is also gain. We edit according to our requirement. This is integration integrator block, just like you can get by searching integrator. You will get this, and then you will implement these equation as this. You can see input here RIV KE theta as like KE minus resistance plus voltage minus KE is equal to inductance. This inductance is 0 because we already know in projected detail. Then we will integrate because our final equation is this integration. After that, by getting integration, we will get kt, and we will add kt plus damping, just like here kt I minus damping, just like this kt minus damping. Then we will add inertia as a gain, then we will again integrate, just like here we'll integrate, and we will get speed. This is the output block. By searching out, you will get this output. I think you can modify by yourself by adding all these blocks in input block, gain block, and edit according the value of ke. This is add block. If you know Simulink, you can make this easily. Then you can mask them into this. So let's check the output. Let's see the output. Output is 0. After system modeling in MATLAB, now we move into PID controllers in MATLAB. From the main problem, the dynamic equations in the Laplace domain and the open loop transfer function of DC motor are the following. S into Js plus B is equal to into theta into S is equal to Kis. Second equation is by Ls plus R into Is is equal to Vs minus Ks multiply theta s. So Ps is equal to theta s over Vs. We calculated theta s and Vs from here. So our Simple equation becomes k over js plus b into ls plus r plus k square. The structure of the control system has the form shown in the figure below. Or this is sum, addition and subtraction from E, we get E, and then we will use controller, we get output, then we will make a plant block, then we will get speed. For a 1 radian second step reference, the design criteria are the following: maximum rise time TR of 0.12 second, overshoot MP less than 4.5%, settling time mean error TS less than zero point 0.2 second, steady state error of 0 for step. Now let's design a controller. We call that transfer function for PID controller is Cs is equal to Kp plus Ki over S plus Kds is equal to Kds square plus Kps plus Ki over S. Now let's go to MATLAB to see the programming of this PID controller. For 1 radian step reference, the design criteria are the following: settling time less than 0.12 second, overshoot less than 4.5%, settling time T is less than zero point 0.2 second. Now let's design method introduce and introduction. PA controller design page, create a new moments of inertia of J is equal to zero point 0.01 kilogram meter square. Motor viscous friction constant B is equal to 0.12 Newton meter second. Electromotive force constant Ke is equal to 0.01 V, V radian second. Motor torque radian over second. Motor torque constant Kt is equal to 0.01 Newton meter or ampere. Electric resistance R is equal to 1.2 ohm. Let's put these values J, V, K, R, L. Now design P using the equations. Using the equation P is equal to K over JS plus B multiply LS plus R plus K square. Proportional control Kp is equal to 10. Let's calculate PID by using PID function in MATLAB. Kp and systematic C system control feedback plus Cp motor C multiply P motor 1 T from 0.12 step to 4.5. Now check step by using step function in MATLAB, system calculation, and then T over T. Let's turn on the grid. Okay, let's check these. Next we will move to PA program is running, so we are discussing one more thing: PID control. KP75 KI1 KD1 figure 2 will get PID controller by using these command. Then we will do system calculation. Then we will calculate the step response. Total should would be PID control with small k and small kd. Next we will tune the gains. So this is our output from these commands. Now we'll move to PID control and let's see the output by using these commands. You can see here like here PID control small ki and next move to tuning the gains. Now kp 100, ki 200, kd1 figure. Large ki we use large ki and small kd. Next let's check the tuning of this PID controller. You can see here same output like before. Now let's check difference other tuning of PID controller with KP 100, KI large 200 and KD also large. Let's check the output using these tuning parameters. You can see now the output is better than others. That was the tuning portion of our project. Now we will move to trial error rules for PID tuning Reagan-Nicholas approaches. Let's check the structure of LMC is equal to this plus minus 2s to ps ds is equal to y, and then we will rearrange above block diagram as rs to ys addition block qcs qs, then again final will be rs qs over 1 minus gs is hence the equivalent PID control port in the block diagram for these part. The method assume that the system has transfer function of the form gs, hence the equivalent PID control port in the block diagram for the second part. The ridiculous tuning method assumes that the system has transfer function of the form kd. The above system is first order system with a time delay parameter. It also record the magnitude of the pulse open loop occurs of the plant output divided by the input in the low frequency to determine the gain parameter. The above system is first order with a time delay parameter. It records magnitude and phase open curves of plant output divided by input at low frequency to determine the gain parameter. Using the values of kV, T, you can easily calculate the PID gain setting by using tuning tools. Now let's check the simulate model of Regnum-Nicholas. So check the first with Kp is equal to 0.6 kd, T is equal to 0.5 T naught, kd is equal to 0.1 to 5 T naught. Method Nicholas 5 0.45 0.6 kcn. Let's check kpt. You can see kc this is the last part, like kc point 5 kc kc Ku is equal K naught is equal to 0.5, K naught is equal to 1.2. You can design this PID controller model, Ziegler Nicholas model by using these commands. Step 1, you can search step. If you want to create this model, you can get these blocks from the MATLAB. First step, you will find step block this. Then you have to add addition block, add block, and you can change the sign of cycle, just putting -1, then apply. Next part will be gain, so we first will be step. You can see here step, and other will be gain, so we search gain block, and we will change the value by double left click on the gain, and we will put the value 1.617, then click on apply. So our next blocks are also gain, so we can copy this, Control C and Control V. So next will be these. So next is integrator. You can use integral, this integrator block. So and other is also sum, but the three addition parameters. So you can add one more by copying previous one. So you can see this is, then is transfer function. So you can get easily by typing transfer function. So you can see This is different. So numerator, denominator. See, you can see the same. You can change the value as like this 1.21. That x is also denominator. The value is 5, 10 like this. So you can copy and you will change the value. Next is transport delay. So you can search here transport delay and you will find this. Next block will be scope. You can search scope here and the delay value should be like this. Time delay 1, initial output 0, and initial buffer size should be. You can, this is a default value. You don't need to change. Other is also for measurement block you need the transfer function here. So in this way you can make the block like this. Connect this and then you have to this just like this and this. Then you need to actually this need to be add here. This should be here above model. This then you need switched derivative. You will need other block. This is switched derivative. So you need switched derivative. Switch derivative for linear. This one. Okay. So you need to add with this block and then you need to add with this last part just like above and this with this and then again the integrator and then delay and this part we need to connect with negative. First we need to connect with output. Need to change the value and then we need to connect with this. That will be same like above. Then you can change the value to tune the model. Like this you will change the value and you will get the output. Okay, so that was the project. That was the project of PID controller design and tuning for DC. Thank you for watching this video.